Okay, I've got a couple of probability models up here for you right now, a couple of probability distribution charts. I don't know, let's say this is, you own this business and you sell these parts. You got two possible customers. You've got the military as a potential customer, and you've got civilians as a potential customer. And these probability distribution charts tell you how many of these things that you'll sell. For example, you might sell 1,000 to the military, chances are only 10% of that happen. You might sell 3,000 to the military, only has a 30% chance. Okay, what I want you to calculate was the mean or the expected value, the standard deviation, and the variance of those three. All right, Mass, let's do expected value or mean. What do we do first? Yeah, just write the formula. On your paper right now should be the formula and then plugging in the numbers, and then we'll talk about how you can get them in the shortcut.
So mean.
Yeah, you can write mu. Now, I gave these letters, you know, the book's real popular on X and Y. I like you giving this is what the value, what the random variable is. So you could say mu of m. You could have also said the expected value of m. That's the way the formula looks. They mean the same thing. And what's the formula for it?
It's the sum of, so it'd be x to the I,
Right.
y to the, or not y.
Times the probability.
Probability of I.
That happened. And I guess I just figured this out. This would actually be m, wouldn't it? I've been teaching 14 years. I didn't realize that's. Usually they name these random variable x. That's why it's x sub I, but I'm doing. Thank you very much. All right. All right. So let's plug in some numbers to see what we get.
So you get 1,000 times 0.1 plus 3,000 times 0.3 plus 5,000.
Okay, you can keep going. Remember, I need 3 of them, so there's only 4 of them. So if you wrote all 4 of them, that's fine. Last period, the person wanted to be lazy. They did this. That's okay too. I just need to see 2 and the last one. So,
10,000.
all right, now how you get the answer to this, I don't care. You want to plug that whole stream into your calculator, that's fine. You can go ahead and do that. But we do know there is a shortcut to calculate the mean of this distribution chart. If you go ahead and in your editor put in the first 2 columns your probability distribution chart, then when you go to calculate, if you enter 2 parameters here, your calculator knows, oh, he was talking about a probability distribution. It's not just going to check down one particular column for the data. That comes out, and we've got our mean of 5,000. Now let's remember what this means now. In the long run, over many, many years, okay, on average, we're going to sell about 5,000 units. Now, in any particular year, I may sell fewer or less, but that's in the long run how many units I expect to sell. Now, if you're a businessman, standard deviation's a big deal. Think about this now. If I have a big standard deviation over around 5,000, some years I'm not going to sell hardly any, or some years I may make a lot. In terms of doing payroll, that's a big deal. If I have a really low standard deviation, I can just about count on 5,000 coming in every year. That's good to know. So if you're a businessman, standard deviation is an important thing to know. All right, so the formula that you have in your green sheets is the variance. Okay, we'll take the square root of the variance later and go get the standard deviation. The formula for that is the summation of the actual value. I'm not comfortable putting it in there. Minus the mean. So how different is that value from the mean? Squared times the probability of it happening. Again, now show me 3 of them. So I might have a big difference. A 4,000 unit difference. Okay, but that's only going to happen about 10% of the time. Plus, I might have a 2,000 difference. That's going to happen 30% of the time. Plus, the pluses actually help here a little bit. Or I might have a 5,000 difference. That's going to happen 20% of the time. Okay, so show your reader that you know how to calculate it. But fortunately, they give me that answer here. Now, what they give me is standard deviation. So if you're asked for the variance, what are you going to have to do with that number? You have to square it, go the other direction. So it's like, what is that, 7.9 million or something? Is that, what is it? 800,000. Now, how to find the standard deviation? You could just take the square root of that, and we've got that number there, 2792.8. That's pretty high standard deviation, almost 2,800 units. If our mean is 5,000, that's some years a lot, some years not so much. Variance 7,800,000, and then standard deviation 2792.9. Okay. Questions on that, Jason? We're good. All right, give me the other ones here. What was the mean on this side? Like 400 something. Oh, by the way, I didn't give you that, but I shouldn't have had to, right? What is that supposed to be? 0.5, right? Because they have to add up to 1 if they're a probability distribution chart. Okay. 445, what was the variance of this guy? Everybody says the same number at different times. You don't get any. What do you got?
19,223.82.
And what was standard deviation?
136.65.
All right. Now, what if I wanted to find out what my total sales are going to be this year? In other words, I want to figure out how many units total I'm expecting to sell. So what I really want to do with these two distributions is add them up. Now, we could do what we did on 44C, what most of you did. I could create a third distribution chart. In that distribution chart, I would have, what, 1,000 plus 300, I'd have 1,300. I'd have 1,000 plus 500, I'd have 1,500. I'd have 1,000 plus 750, I'd have 1,007. I'd have all those different possibilities that could happen, and I'd have the probabilities of each of them. I could then go through this process to find the mean and the variance and the standard deviation. However, okay, there is a shortcut. Okay, and that's right here. Whenever you're adding or subtracting random variables, if you know the means of the individual random variables, to find the mean of the combined, all you have to do is add them together. Go back to 44 that you did last night, right? It would be a lot easier just to add up the 2.5 and the 4.5 to get to 7 than to create that new distribution chart. So what would that look like? If I was calculating the mean of M plus C, I'd say it's the mean of the M plus the mean of the C's. In this problem, it'd be 5,000 plus, this is to show the work part. So in the long run, I expect to sell 5,445 units. All right, now's when things get weird. What if I want to find my new combined standard deviation? All right, this is the formula that we use to find the variance. Okay, first things first. Cannot use this formula unless these two events are independent of each other. Remember what independent means. If I know how many military units I sold, does that have any effect on the civilian? If that answer is no, then we know those two events are independent of each other. This only works if the random variables are independent. Like let's say this was SAT math and SAT verbal. Well, I know of good students that usually do pretty good in both, and bad students might do pretty bad in both. There may be some slight variation. But if I know somebody did great in SAT math, does that mean that they probably did a little better in SAT verbal too? Probably. So those would be dependent events. You couldn't use this formula. There's another formula. You're not responsible for it. It gives me a headache even looking at it on 421. So if you look in your book at 421, just know you're not responsible for that formula. But that's the crazy formula we have to use if they were dependent variables.
It's on the green sheet. It's on the green sheet also.
So go look at 541. That formula you're not responsible for. It's got correlation in there. It's got all kinds of craziness in there. Okay, so don't worry about that one. We'll only be doing random variables that are independent of each other. All right, so here's the deal. Oh, excuse me. Here's the deal. Whether I'm combining these random variables by adding them together or subtracting them, if the two random variables are the same, I can find the variance by adding the individual variances together. And to take the square root, I would take the square root of that. Please remember this. I got a little trick question coming for you later. That's the formula that you need to use. So if I was trying to find the standard deviation of these two variables added up, it would be the square root of the variance for military plus the variance for civilian. So this would be the square root of 7,800,000 plus 19,223. Plug that in your calculator and you'll figure out how much they differ on average from 5,445. Okay? Still laughing at my voice?
She cried. There were literal tears.
Okay. All right, I got to go back and review some from chapter 1. This like blew period 3's mind. They think like they'd never seen this before in their life, but here, hopefully some of you will remember. Let's say I have a bunch of numbers. This is my number line. My numbers go from like 2 to 12, let's say. And I add a constant to all of the numbers. Will my mean change?
No.
Oh, come on! I'm the middle! I'm the mean! Come on! I got these numbers 2 through 12. Let's say I add 10 to all of them. Now I've got numbers from 12 to 20. Did the mean change? But did the standard deviation change? No, I didn't get any more spread. So adding a constant, the mean changes, standard deviation does. Are we remembering that? Now how about multiplying by a constant? So I've got 2 and I've got 12. Let's say I multiply by 10. Okay, well then, you with me? I picked weird numbers, right? So this goes to 20, but this goes to 120. So does the spread change? And does the mean change? You're scared to answer. Did I move? I got a bunch of numbers, 2 to 12. I multiply them all by 10. Okay, so we've done this before. That's all this junk. It's a whole bunch of ugly symbols. Okay, but here's what it means. Let's say in this problem that I'm making like $3,500 profit on each unit I sell. I could go create a new distribution chart by multiplying that by 3,500. That would tell me how much money I made. Multiply that by 3,500. Multiply that by 3,500. And then I could go through all this work again. Or what this is telling me is if you multiply everything by the same constant, all I need to do to find my new mean is take the old mean and multiply it by that constant. So for this particular problem, if I'm taking 3,500 and multiplying it by the military distribution, I can simply take that 3,500 and multiply it by the old mean, which is 3,500 times 5,000. And I'll figure out how much profit I'm going to make in the long run per year. Okay, I don't have to go create a new chart. If I said, you know what, I overestimated on all these guys. They're really 100 less. So that'd be like subtracting a constant from all of them. Okay, I can simply take my old mean, and so what am I doing? I'm subtracting 100. That's just like taking that mean and subtracting that 100. The old mean was 500, so the new mean would be 400. All right, where things get a little bit interesting is the standard deviation. If I multiply this by a constant, is my standard deviation going to change?
Yeah.
If you multiply by a constant, will the standard deviation change?
Yes.
I get nods from everybody. I'm here! Right? So a weird looking formula here. Don't freak out by it. Okay, so if I was looking for the new variance, I would take the old variance and multiply it by 3,500 squared. That's what this formula is telling you. But if you're trying to find the standard deviation and you took the square root of it, it would just be the 3,500 times the new standard deviation. Okay, so if I'm trying to find my new standard deviation, it would just be 3,500 times that. If I was trying to find my new variance, it would be 3,500 squared times that. Will there be any changes over here when I just subtract by 100? Will the standard deviation or variance change when I just subtract by 100? The answer is no, because they all stay the same. Okay? So a lot of ugly looking formulas in your book. This stuff we did before. This should not be hard for you. This is kind of the new thing. So I could be given probability models and being asked to combine them by adding or subtracting them, find the new mean, standard deviation, and so on. There's something else they may give you. If you get a distribution not written like this, but as a normal distribution, and you have another distribution that's normal, when you combine them, you will create a third distribution that will also be normal. Let me give you an application for that. All right, Winger and I are going golfing, and we're teammates. Winger, when he golfs, all of his scores turned out to be kind of a normal distribution. And on average, he gets, I don't know, 110. You guys got it. That's good. It means he's bad. And he's consistently bad.
What's that?
It's a 3. Okay, so that's Winger. All right, he's going to golf with me. We're going to be partners. I average, I'd say, about a 68. And I'm consistently good. That's good. That's really good. All right, so we're teammates. Okay, and what we're going to do is we're going to take our combined score. Now here's what I'm going to ask you to find out. We need a score of 174 or better to win this tournament. What is the probability that we win this tournament? Go.
You say 174.
Yeah, we're a team, so we're going to add our scores together. So we're taking the distributions, we're adding them together. Now when I have one distribution of scores that are normal and another distribution of scores that are normal, when I combine them, what I'm telling you is you still have a normal distribution. 174 or better will win the tournament. I want you to calculate for me the probability of winning the tournament. So you're going to be drawing a normal curve, you're going to be doing z-scores, you're going to be doing shading, you're going to be looking at your charts. Okay? Get going. 174 or better, which in golf that means or lower, right? Better scores lower, will win the tournament. You can assume that we are independent of each other. In other words, if I know his score, it doesn't affect my score. That's a big statement I just made in terms of your calculation. Each other out. What happens when you combine distributions? Can you figure out what the new mean and standard deviation would be of our combined distribution chart? Trying to figure out how many standard deviations we have. All right, now shade your region. 174 or better wins the tournament. We want to know the probability that we win the tournament. Seeing some good pictures out there. Remember, show me what I need, no more, no less. Write your formulas down. Now you got to write your C-score formula. I said 174 or better wins the tournament, so where's 174? Do your shading. Go calculate things you need for your z-score. Go look it up in your tables. The key concept here is if I have two normal distributions and I combine them, I'm still going to have a normal distribution of scores.
Shots like that. Shape is
Are you always adding the separate variances even if you're subtracting?
Yes, I'll talk about that in a second. That's key.
Okay, let's work this together now. What I told you is that if you have separate distributions that are normal and you combine them in some way, either adding or subtracting them, you're going to have a normal distribution of combined scores. So here's our combined scores with Winger and Ricewig. We should expect in the long run to get, this is the guy that kicks in here. Okay, I don't have to create any distribution charts or anything. I can take the mean of one of the person, mean of the other person, and just add them together. So adding these two together, I get what, 178? I said a score of 174 or better would win. Here's our number line. Here's 174. In golf, less is good. So that's the probability of getting a score of 174 or lower. Now our job is to go find that z-score. Our z-score formula is the actual value minus the mean divided by what a standard deviation is. So 174 minus 178, and here we get to the part where I hope you got the right answer. I hope nobody has got a 7 there. Did you have a 7 there? Can you add the standard deviations together? You cannot. In order to calculate my new standard deviation, you have to add the variances together and then take the square root. So in this particular problem, the variance of Winger plus Ricewig is the variance of Winger plus the variance of Ricewig. The variance of Winger would be 9, right? 3 squared. Variance of Ricewig would be 16. That's 25. So the variance is 25. In order to find the standard deviation, I need to have the square root of 25. So therefore, the standard deviation was 5. Okay. So I believe that's what, negative 0.8. Put that on your chart, and that's about 21% around there, 21 point something percent. So we got a little bit better than a 21% chance of winning the tournaments. Questions? All right, Zane came up with a good question. What if instead of combining the scores, let's say we're playing in some kind of weird tournament where if the difference of our score is less than 30, difference of our scores is less than 30. Okay, I want to think about what would change here. So now we're doing Winger minus Ricewig. That's the distribution we're looking at. What would change? Would the mean change if we were doing Winger minus Ricewig? Now you bet it would, right? This is plus or minus over here. So Winger minus Ricewig would be, I don't know, is that 42? So this would be a 42 here. Now would the standard deviation change if we were doing Winger minus Ricewig? This is the tricky part. Would the standard deviation change? And the answer is no. Okay, to find my new variance, it's always adding the old variances, no matter what we were doing with those distributions to start with. Okay, that's a tricky thing you need to remember. It is kind of on your green sheets. We're going to show them more. I'll show you more about that later, but that kind of stuff is on your green sheets where you can see that. Okay. This also holds. Let's say I had 4 people running a relay race, and their combined time was going to determine if they won the race or not, like cross-country teams or whatever. So say I had one runner, and his average time was, 27 minutes with a standard deviation. I had another runner, his average time was 26 minutes with a standard deviation. I have another runner, his average time was, 28 minutes with a standard deviation. If I was going to combine the 3 and try to figure out if they won the race or not, you just carry on this to 3. There's 3 of them you add up. And you just carry on this as well. Variance of one plus the variance of the other plus the variance of the other. That's my new variance. Take the square root of it, it would give you the standard deviation of all of them. Okay, last thing for the chapter, but a lot of stuff here. This is just linear transformation. Okay, hopefully you can remember this. This is the new stuff. If I have distribution charts, I don't have to create a big third chart. I can find the mean, standard deviation, and variance just using those formulas. Or if I have normal distribution. Okay, and I combine them, I can use those as well. Key thing I want you to remember. This formula always works. Whether they're independents or not, you can find your new mean. But you can only use this formula if you know the two events were independent of each other. First couple of problems you do for homework tonight, they're just asking you, are the events independent or not? Remember your test, if I know the value of one, does it affect the next? Yeah.
So they're dependent. Is there any way we can figure that out?
Well, there's some mathematical ways, right? If I ask you, are these independent or not, remember you could multiply these two together and see if it equals. There were some mathematical ways. We learned how to do it last chapter. For this chapter, they're just going to say, do you think these two events would be independent or not? And remember, what's our test? If I know one thing happens, does it affect the next? Okay? All right, assignment 4.